Thank you. Thanks for the introduction, and thank you to the organizers for organizing this very interesting conference and giving me a chance to speak here. So this is going to be a continuation of Mahan's talk. I'll start with a quick recap of some of the things he talked about, and then I'll try to furnish some proof details of the theorems that he mentioned towards the end. And right at the end, I'll try to describe a purely Teichmüller theoretic application of this entire framework, because the framework that Mahan has been talking about is essentially a combination theorem for two different kind of objects. One side is coming from Fuchsian group, another side from rational dynamics. But once we set up this entire thing, I'll try to describe how one can reap benefits from this entire framework purely in the Teichmüller theoretic setting. But that's at the end. All right, so let me quickly recall the whole framework of combining Fuchsian groups with polynomials. But before that, maybe, let me say a few words about the initial motivation, although Mahan said, I think, spent enough time on motivation, but there was maybe one thing that I should say on Fatou's, there was a quotation by Fatou that was shown in Mahan's slides, one of the first few slides, where Fatou said that one should look at the space of algebraic correspondences in order to find a unification of rational dynamics on the Riemann sphere and Kleinian groups or Fuchsian groups. So why algebraic correspondences? So I should at least say that it's not difficult. The point is the space of all algebra. So firstly, what is an algebraic correspondence? This was mentioned. It's a multivalued map from the Riemann sphere to itself, but there's maybe a slightly more systematic way of looking at it. One could either think of an algebraic correspondence of finite by degree as a multivalued map. That means every point has finitely many forward images and finitely many backward images. For instance, something like W equals square root of Z would be an example of an algebraic correspondence. Given a value of Z, you have two forward images. Or you can think of it as the following thing. So suppose you have C hat here, a Riemann sphere and a Riemann sphere. All of this is true in much more generality for complex manifolds, but let me stick to this situation. And this is the product space C, Riemann sphere across the Riemann sphere. And suppose you have an algebraic curve here. So this is the algebraic curve, which is the solution of this polynomial in two complex variables. And you have a pi1 first coordinate projection and a second coordinate projection here. Then the algebraic correspondence is essentially defined as pi1 inverse followed by pi2 restricted to this algebraic curve C. What does that mean? If you pick a point here, say Z, there are finitely many, you plug in that value of C, say Z0, so you plug in that value of Z0 over here, and there are finitely many points Z0 comma W on this curve, or finitely many points whose first coordinate is given by Z0, and you project them down by pi2, and those are the images. So that's another way of thinking about it. If you want to write this as an algebraic correspondence with this definition, you just write it as W square minus Z equals 0. That is the algebraic curve, right? Okay. Every rational map is an algebraic correspondence. Every point has one preimage and D many backwards images, where D is the degree of the rational map. Every finitely generated Kleinian group, suppose you have a Kleinian group gamma generated by gamma 1 through gamma k, that also gives rise to an algebraic correspondence. I'll only write down the algebraic curve, but using this, the algebraic curve will give rise to an algebraic correspondence. And the algebraic correspondence here is also quite simple. It's just this thing. So given a point Z, there are k solutions to this algebraic curve, k points on this algebraic curve whose first coordinate is Z, namely gamma 1Z through gamma kZ. And that's exactly the dynamics. under the full dynamics of the group, the point z goes to gamma 1z through gamma kz. You can assume that this is a symmetric set of generators, so there are k many, say, or even if it's not for a symmetric, there are k forward direction and k backwards direction. Okay, so that means algebraic correspondences can be thought of as a much larger world or a much larger galaxy in which these two different planets, the rational planet and the Kleinian planet, live. And so the target or the goal is basically to come up with another planet where you have some species from these two planets, and they interbreed, and then you want to understand that planet, the creatures of this planet and what the parameter space, what the planet looks like. Right, now the recipe that Mahan described involved 4 steps, if you think about it that way. The first step was a trade-off where you realize that a group has a lot more structure than a rational map. It's invertible, whereas a rational map does not have well-defined inverses. You can choose local inverse branches, but there is no global inverse to the map. Instead, you want to reduce the group to some single-valued map, and that's what Mahan said. That's the example of a mateable map. So from the group, you want to pass to a one-variable map. That was step 1, and Mahan gave 2 examples. The first example was given by these Bowen series maps of punctured spheres. Mahan drew the example of the triply punctured sphere. Let me show you the example of 4 times punctured sphere, exactly the same recipe. This is a fundamental domain of a 4 times punctured sphere. The generators are G1, G2, G3. They pair the sides this way. And then your map is defined as G1 in this pocket, G2 in this pocket, G3 here, and the inverse is over there. And it's easy to check that this map is, well, it's a piecewise Mobius map. It turns out to be a circle covering that is conjugate to z to the 5. In fact, if you look at this endpoint over here and this one, these 2 are fixed points. The other 4 ideal vertices, so this point, so G1 sends this geodesic to that geodesic, hence this endpoint is fixed. Same is true for this guy. But this endpoint here, this ideal vertex maps to that under G1, and since here the map is G1 inverse, this guy goes back there. So these form a 2 cycle, these form a 2 cycle, and then just using these facts, you can check that it's a covering of degree 5. Topologically conjugate to z to the 5. And it's orbit equivalent to the groups, so it's a mateable map in the sense of Mahan's definition. He also talked about factor Bowen series maps. Let me give you another example of a factor Bowen series map, just to I'm sure. Let me work out another case. So what exactly is a factor Bowen series map? In a factor Bowen series map, you are trying to give up on some of these conditions. At the end of the day, you still want an expansive circle covering. You still want a circle covering that is compatible with z to the d, but you do not necessarily want piecewise Fuchsian or piecewise Mobius. Piecewise analytic is good enough, and maybe you want to give up on actual orbit equivalence to the group. You want to allow some sort of finite index business. So it'll be like a virtual, you can call it a factor Bowen series map or a virtual Bowen series map. So what exactly is happening? The philosophy is this: you start with a surface, say the Hecke surface over here. If I chose pi over 3, this would be exactly the modular surface. So this guy has a cusp, an order 2 orbifold point. So this is pi because the surface has 2 sides. So there's a pi over 2 on this side and a pi over 2 on the other side. So this is an order 2 orbifold point, and this is an order 4 orbifold point. So this is just 1 degree higher, or it's the Hecke group after the modular group. The problem is that if you look at its fundamental domain, you can choose a nice fundamental domain. This is a fundamental domain for the Hecke group, where rho is just the rotation by pi over 2. It takes this radial line to that radial line, that's the side pairing, and sigma is a Mobius involution on this red geodesic. So if you fold up, you get exactly this thing. The 2 green things get identified and give you a geodesic from cusp to the order 4 orbifold point, and this red gets folded, the midpoint becomes the order 2 orbifold point, and the whole geodesic becomes this guy. The problem is if you apply the recipe of Bowen and series, if you write down the formula of the Bowen series map in this context, it will not be a continuous map. It's in fact, it's not even, well, it's not going to be a continuous map. There are certain choices. In fact, in the definition of Bowen series map, there are certain choices. I want to push that under the rug. There are certain choices involved, and the punctured sphere case, in some sense, is a fortuitous situation where everything you do not have to make choices, and the thing turns out to be a covering map. Here, you're not that lucky. The Bowen series map is not going to be well-defined or continuous. That's precisely because your fundamental domain ends in the disk. The good situation over there in the punctured spheres case was that all the ideal boundaries, all the boundary points were at infinity. Here, that's not true. You have a vertex inside. So what you want to do is somehow you want to pass to a situation where you have an ideal polygon as the fundamental domain. And to do that, you want to pass to a cover. So the cover is just this guy, where you take this cusp to pi over 2 geodesic, and you rotate around it. So you take a cyclic 4-fold cover. And then, since you're rotating around this guy, there's only one cusp on the cover. The pi over 2 thing has been resolved. The order 4 orbifold has been resolved. That's no longer a special point on the surface. But you have created 4 of these order 2 orbifold points because you glued 4 copies of these things. That's the cyclic 4-fold cover. And clearly, the fundamental domain is, it's a cover. The cover essentially consists of 4 copies of this. So the fundamental domain can be chosen to be, can be obtained by patching 4 copies of this thing over here. This ideal polygon, this ideal quadrilateral, is a fundamental domain of this cover. And for this guy, you can actually write down the Bowen series map. And well, the Bowen series, so what is a formal definition of a Bowen series map? It's basically, you write down the fundamental domain, you write down the side pairing transformations, and use those side pairing transformations to define the map in the appropriate pockets. So here, for instance, this is a quadrilateral. The side pairings are just given by the same sigma here, and then it's a rotation. You just conjugate by rho to get side pairings for these 4 geodesics. And the Bowen series map is defined as sigma in this half plane and the conjugates on the appropriate half planes. So this at least allows you to write down a Bowen series map that's well defined. The issue is that it has minor discontinuities at the 4 corners. And that's exactly the reason why you need to pass to a 4-fold quotient. When you pass to a quotient, the good thing about these 4 points of discontinuity is that when you go towards any of these points of discontinuity, the left-hand limit and the right-hand limit are also in the set of these 4 points. So when you identify all of them to the single point, you're forcing the map to be continuous. So that's roughly the idea. You start off with a surface. You pass to a cover. You're going up step. Then you associate the Bowen series map of the cover. But you have to do something, negate the effect of going up. And that's basically what you're doing by passing to a quotient. And you get this factor or virtual Bowen series map. Right, so you could do this for pi over 3, and then that's what will give you the Bowen series map, or the factor Bowen series map of the modular group, which is important. This is related to the question that John asked earlier, whether we get back the Bullet-Penrose framework of correspondences. The answer is yes, and one has to start off with the factor Bowen series map of the modular group to do that. Okay, so these are examples of circle coverings associated with groups. Step 2 was a simultaneous uniformization step. Sorry. So on one side, so you start with one of these Bowen series maps or factor Bowen series maps, and you look at its degree on the circle. This guy has some degree, and you take a, for simplicity, let me just stick to Blaschke product. So what is a Blaschke product? Everybody knows, let me still recall. A Blaschke product is a proper holomorphic map of the disk. And there's a concrete algebraic formula. these objects are, morally speaking, analogs of Fuchsian groups because they have under a genericity condition, their Julia set is the entire circle, and they have two components in their domain of discontinuity, just like a Fuchsian lattice. So simplest example is z to the d. So you take a Blaschke product of degree d, which is this d is chosen to be the degree of the factor Bowen series map on the circle. So these are the two objects that you want to combine. I'll not go through the whole process of combining, but just to recall, the idea was to first construct, or by definition, this guy is topologically conjugate to z to the d, and a Blaschke product is also topologically conjugate to z to the d on the circle. That allows you to choose a conjugation on the circle. It's a simple point, but it's good to emphasize this conjugation is only on the circle. The dynamics of the Blaschke product on the disk and the dynamics of the Bowen series or factor Bowen series inside are completely different. We are only requiring boundary compatibility because we have two half planes and we want to glue them in an equivariant manner. Once you do that, you take this, in my picture, I think right now, yeah, the disk, the action of B lives inside. So I'm drawing really, in this picture, I have a Riemann sphere, which is obtained by gluing this this copy of the disk and that copy of the disk. Inside, you have a B action, Blaschke product action. Outside, you have the action of the Bowen series map. But this is a topological object, and using some analytic machinery, which I, again, do not want to get into, you can uniformize it. You can put a complex structure so that this map becomes a complex analytic map. And then things will no longer look so nice. So this is also true for the standard quasi-Fuchsian setting. You take two Fuchsian groups, you can glue them together topologically, but then when you uniformize it, the limit set becomes a Jordan curve, but it's a quasi-circle. It's no longer a round circle. Same thing will happen here. The boundary of the two different domains that you patch together is going to be some Jordan curve. Here, it's not even going to be a quasi-circle because of something that Mahan mentioned, the map B. If you just think of z to the d is an expanding thing. All the periodic points are repelling, or they're expanding on the circle, whereas in all of our examples, the Bowen series maps or the factor Bowen series maps, they have parabolic points. It's a complex analytic fact that when you try to glue a repelling dynamics and a parabolic neutral dynamics from the other side, you do not get a quasi-circle. You get cusps. So that's what's suggested in these cusps. Anyway, this is what we will call the conformal mating. So far, there are no correspondences. This was our step 2. We went from a group to a single variable map on the single valued map on the circle. Then we combined a Blaschke product with that map, uniformized to get a conformal mating. The only property of the conformal mating that one should keep in mind is that there is an analog of a Julia set or a limit set, the black region, such that inside the dynamics is conformally conjugate to the Blaschke product. Outside here, the dynamics is conformally conjugate to the Bowen series map A gamma. And recall that the map A gamma is not defined in the hexagon. It's only defined on the union of these 6 half planes. So when you glue them, combine them topologically and straighten, you get a map that is defined. So it's defined inside, it's defined on these brown half planes. But here by half plane, I mean these regions, where one boundary curve is this brown guy and the other boundary is the black fractal. But the map is not defined outside. So it's this complex analytic mating, it's combining a Bowen series map with a Blaschke product, but it is not a global map. And it should not be a global map because a conformal map or a holomorphic map of the sphere is a rational map. If you cannot possibly expect to put a group dynamics and the dynamics of a rational map into a single rational map. You want something more, something richer. So this thing is potentially richer. This map is not defined on the whole sphere. It's some partially defined analytic map of the sphere. But our target is to go to an algebraic correspondence. So while analyticity is good, Usually when we do either rational dynamics or Kleinian group, we look at global objects. A Mobius map is analytic on C hat. A rational map is also analytic on C hat, but C hat being a compact Riemann surface forces these objects to be algebraic. Here, the domain of definition is this brown guy. The domain is the region bounded by the brown region. So it is not defined on a compact Riemann surface. Therefore, nobody tells us that this conformal mating that we constructed has any sort of algebraic property. It's just an analytic map. Yes? Hmm? Yes. They're coming from the 6 parabolic points. These, no, and their grand orbits. So the pre-images and their iterated pre-images, so countably many of them. Okay. Right, okay. So step 3, which was sort of implicit in Mahan's slides, is a way, it's, if you like it, it's a kind of gaga without compactness. You want to go from an analytic geometry to an algebraic context without compactness. So you want to say that the conformal mating that you constructed here, over here, is an algebraic map. So this is a passage from analyticity to algebraicity, and this cannot come from nothing. It cannot come, from thin air. So we need something, and that something is this observation that here, the Bowen series map is of order 2 on the brown region. A point here goes there under G1, and then under G1 inverse it goes back. So it's an order 2 map on the boundary. The same is true here as well. If you look at how the Bowen series map acts here, sigma is an involution on the boundary. All of these maps are involution, and this property is preserved under the quotienting procedure. So the map, that Bowen series or factor Bowen series, these are involutions on the boundary of the whole. After uniformizing, this soft topological property obviously survives. So the mating that you constructed has this interesting property that, what is it? If you axiomatize it, what you're looking at is a map from some subset, a closed Jordan disk in the sphere to the whole sphere, such that F is continuous. It's meromorphic or analytic on the set, and if you restrict F to the boundary, firstly, the image of the boundary is the boundary, and this is an involution. So it's an order 2 map. This is the source of algebraicity. So the statement, this is actually a theorem, which says that whenever you have a map of this sort, you need to make some assumptions. The boundary of this guy has to be nice. The boundary of omega, it is nice in our case because remember, these things actually came from hyperbolic geodesics. So these are real analytic curves. So if you take a Jordan disk omega, such that its boundary is piecewise real analytic, and you have these properties, and a fourth property that, which let me not write down, there are some singularities, but the singularities are preserved as a set. So remember, the Bowen series map, the Bowen series map preserved this guy, fixed that, and paired these two singularities or ideal vertices and paired these two ideal vertices. So here, these bad points where the boundary is no longer singular, or no longer non-singular, it's a finite set, and this set is preserved by the map F. And if these conditions are satisfied, then the statement is that, right here. The statement is that such a map is necessarily an algebraic map. Not only that, the proof is constructive, you can write down an explicit algebraic description of the map. So let me tell you what the idea is. If you have a domain, so for instance, this kind of a Brown domain, and you have a meromorphic map defined on it, extending continuously to the boundary as an involution, what would be the first example of such a map that should come to your mind? The map is 1 over z. If you take the disk and look at 1 over z, it's a trivial example of this sort of a map. It's an involution on the boundary, and it's holomorphic inside. So in some sense, we want to say that all such maps are modeled by this kind of behavior. The thing to keep in mind is that under 1 over z, this Brown curve is preserved under the map F. So you're trying to model it by some Jordan disk whose boundary is preserved by 1 over z, and it's an involution on the boundary. Now, it is not true that the circle is the only set that is preserved by 1 over z. In fact, if you take the 2 fixed points of 1 over z and take whatever curve you like in the upper half plane, apply 1 over z, you'll get something like this. By choice, by definition, this boundary is preserved by 1 over z, and 1 over z is an involution on it. So I do not want to say that I'm trying to model this action by 1 over z on the unit circle, but I want to say that I'm trying to model the action of the map on the right side by 1 over z on some disk that is mapped inside out and whose boundary is preserved, not necessarily the round disk. So that's the statement. Whenever you have a map like that, there exists a pair, R and D, where D is a Jordan disk which is mapped inside out by 1 over z, and a rational map, a global rational map, that sends this disk to the Brown domain here, the entire domain. So R, in some sense, is a uniformizer, but uniformizer in a slightly loose sense. Usually the uniformization is by the round disk. Here I'm only saying that it's being uniformized by a disk that is 1 over z, whose boundary is 1 over z invariant. The thing goes inside out, not necessarily the round disk. Okay, but the key thing is the algebraicity of R. So I can find a rational map R and a disk like this, which is mapped inside out by 1 over z, such that R sends this disk homeomorphically to this Brown region. And what do I mean by the map being modeled by 1 over z? I mean this. The action of sigma is actually given by, first you go back from here to the disk by the inverse branch of R, then you do 1 over z, and then you apply R. So here eta is 1 over z, eta is 1 over z. That's the point. So any map having these properties here on the board and some nice regularity of the boundary is given this way. So the proof of this fact is not trivial, but also not super complicated. Let me just say it in words instead of writing it. The idea is you want to construct a rational map R, and you want to construct a domain. But where are you going to get the domain from? Essentially, you want to take a double or construct a Riemann sphere out of this particular domain. So you want to take 2 copies of this region bounded by the Brown curve. You want to take 2 copies of that, and since sigma is an involution here, it's a self map, you want to weld 2 copies of these 2 Riemann surfaces to build a sphere. There's a little bit of care you have to take because sigma, so well, people here are familiar with the classical welding theory. Welding is possible when you use an analytic map to weld 2 real analytic curves, but the map sigma does not extend analytically in a whole neighborhood, because remember the Bowen series map was defined as some Mobius map here and some other Mobius map there. There is no global analytic continuation. So sigma is not analytic in a full neighborhood. So there are these bad points where the welding doesn't really work. So when you glue or weld 2 copies of this Brown domain using sigma, you could potentially get a surface with boundaries. You still get a genus 0 object, but these points, they could become holes. It could become an infinite type surface. And you have to work a little bit to prove that what you get, the welded surface, is not an infinite type surface. That essentially comes from, well, from the mapping properties. So there are 2 ways of proving that something is not infinite type, or a hole is a hole, not a puncture, that a boundary component is a point or a puncture, not a hole. You could either run an extremal length argument, or you could try to come up with a nice meromorphic map, finite degree meromorphic map onto a punctured sphere, which will tell you that the target is, the domain is a finite type surface. So we use our knowledge of this map sigma to prove that. And that's what gives this algebraicity result. All right, so this is what is the upshot of this slide. The conformal mating has this algebraic description in terms of a global rational map and 1 over z. It's modeled by 1 over z. Once you have that, you want to go to the correspondence. And maybe I should clarify a few things here. Yes. So, yeah, you weld 2 copies of this Brown region, so you get a genus 0 object. That it's one thing to prove that this genus 0 object is the Riemann sphere, or punctured Riemann sphere. These finite 6 points, these are on the welded surface. You want to show that these are points. So the welded surface is a punctured sphere, not a sphere with hole. That's one argument. But once you have that, the Brown curve itself, the surface that you got is obtained by 2 copies of it. One of them is D. And since you're gluing 2 things which are exactly the same, there is a build, and the boundary identification is an involution. This particular Riemann surface comes with an involution. And on the Riemann sphere, every involution is 1 over z. That's okay, once you have the algebraic description of the conformal mating, you want to globalize it. You want to go to an algebraic correspondence. So this conformal mating on the right side is analytic, not defined on the whole sphere, but as Mahan mentioned, somehow we want to find a way to globalize this object, and this is the way. So what exactly is the correspondence? So you want to lift this dynamics of the conformal mating. The point is, why do I really want to go to a correspondence? Is it just because Fatou told us? No, here we paid a price. In order to construct the conformal mating, we dropped the invertibility feature of the group. We passed to a single valued map and mated it with a Blaschke product. But really, we wanted to see the full structure of the group. And you cannot see the full structure of a group in a single valued map. You can only see the full structure of a group when you're working with something that is multi-valued. And that's why we want to pass to a correspondence. So how do you pass to a correspondence? Roughly speaking, you just lift the dynamics of sigma under the rational map. So on the right, this is your conformal mating plane, which is obtained by combining the Blaschke product and the Bowen series map. On the left is a pullback of that thing. Pictorially, this is what it looks like. But what exactly is the correspondence? What is the multi-valued map? What is the algebraic curve that defines the correspondence? Well, so sigma, thanks to our algebraic description, has this kind of a formula. And when I say I want to lift it by R, what I really mean is I want to take a point here and I want to prescribe what the forward images are. That's what it means to define a multi-valued map. You give me a point, I have to tell you what the forward images are. So you take a point, you go forward, and this is how I'm going to do it. I'll take a point here, I'll go forward by R, I will apply sigma, and then I'll come back by R. When I come back by R, it gives me a multi-valued thing. So that's essentially, formally speaking, conjugating sigma by R. So my correspondence is, first you go from the correspondence plane on the left to the conformal mating plane by R, then you apply sigma, and then you come back. let's not make a fuss about what the inverse branch is. It's a correspondence. You're allowed to take all possible inverse branches. But what is this formula now? Sigma has this description. Then, this is an inverse branch. This is not a multivalued guy. This is an actual inverse branch. So these two things will cancel out, and you'll only be left with, is there any other colored chalk here? Yeah. So you'll, at the end of the day, only be left with this. So this is what defines the correspondence. You give me a point Z, and the multivalued map is given by Z going to R inverse of R of eta. Okay. So these are the possible values of W. Z goes to these many values of W. If you, depending on how you want to think about it, if you want to write down an actual polynomial equation that defines this algebraic correspondence, that is going to be, move R over to the other side, is going to be R of W is R of eta is 1 over Z. 1 over Z. This is the algebraic formula that would define your correspondence using the two first and second coordinate projections. Or, if you want to think about it a little more complex analytically, the correspondence is really defined by 1 over Z and the local deck transformations of the rational map R. This is just locally speaking going by R and coming back. So the local deck transformations of the rational map R and 1 over Z generate the correspondence. And since a correspondence has finitely many forward directions and finitely many backward directions, it's a matter of bookkeeping to see exactly what the dynamics is. I don't want to work that out, but if you believe me, this is what the dynamical plane looks like. So this, yeah, I'm accused of not knowing what is blue, telling blue from green, so I don't know, let me call it green. So the preimage of the green region is this k tilde here and the k tilde outside. This is where, remember, this is where you saw a Blaschke product action. And here, on the correspondence plane, a correspondence is multivalued. You have to, on this k tilde, you can organize these branches. So, yeah, what is it? I should say what a branch of a correspondence is. At any given point, correspondence has finitely many branches, but maybe you can, locally, you can take a small neighborhood where these are holomorphic maps. And on k tilde, you can analytically continue one of these branches to get a map from k tilde to itself that is conjugate to B. So one of the branches, since a holomorphic correspondence has, or an algebraic correspondence has many forward branches, and B is a single valued map, B will be encoded in one of the branches of the correspondence, whereas the pullback of the group region, which is outside, where you see the A gamma action, it is a bit like John's earlier example. The domain of discontinuity of this correspondence has finitely many components. There are exactly 6 components. This number 6 comes from the fact that I'm drawing the picture for a 4 times punctured sphere. But the point is, the correspondence acts on the bouquet of these 6 Jordan domains as conformal automorphisms, properly discontinuously. And if you take the quotient, that's the statement here. If you, right, let me back up. So suppose you take a surface for which which is either a punctured sphere or something for which a factor Bowen series map is defined. I think I forgot to define S. Anyway, so there's a collection of surfaces that admit continuous Bowen series maps and continuous factor Bowen series maps. So let sigma be one of those things, and let B be a Blaschke product of degree D, where the degree is just the degree of this factor Bowen series map. Then everything that we did produced for us an algebraic correspondence that combines the action of the Blaschke product B and the Fuchsian group, in the sense that, I already said, on the green region, on K tilde, a suitable branch of the correspondence will be conjugate to B, and on these 6 regions, the correspondence acts, the branches of the correspondence act as conformal automorphisms. You look at the group generated by these conformal automorphisms, it acts properly discontinuously. You can take a quotient, the quotient is going to be exactly the surface that you started off with. In that sense, this correspondence, the dynamics of this correspondence contains the action of the Blaschke product as well as such a surface. If you ran this entire argument on the modular group, you would get back this formula that I wrote here, this formula. This would give you the bullet pen rose example. All right. I think so far I have been essentially amplifying or elaborating on what Mahan already talked about. So one more slide of the same sort. But this is important because what this allows us to do is, I think it's related to something Subhojoy asked earlier. You can combine the action of any punctured sphere. For now, let's forget about things with orbifold points. Let's just look at punctured spheres. So you can take a punctured sphere, look at its Teichmüller space. You can combine any Blaschke product with anything over there. That gives you a product space. It's actually a topological product. And this entire thing lives in the space of correspondences, where the space of correspondences are parametrized by these rational maps. So in that sense, the space of, so what is the character variety for us? The character variety where the entire thing lives, the combinations of Blaschke products and the Teichmüller space live is these correspondences. It's the space of correspondences. What are they parameterized by? What is the parameter space? The parameter space is exactly this rational map R. What you're doing is you take a Blaschke product B and you take a Fuchsian group gamma in the Teichmüller space of a punctured sphere. This entire combination framework gives you a correspondence which is encoded by this rational map. And that's, so the space of, and the degree of this rational map is, well, it's basically, I think, I forget what it is, but it's one more than the degree of the Blaschke product B. Doesn't matter. So the point is, if this is degree D, then this belongs to the space of rational maps of degree D plus 1 of the Riemann sphere. So the space of correspondences is parameterized by this quasi-projective variety, but now my rational map is not a dynamical object. The dynamics is really generated by the deck transformations of R and 1 over Z. R is just an intermediate object that gives rise to the correspondences. Okay, so towards the, I think maybe on his last slide, Mahan stated that one would like to go to the boundary of these Bers slices. First thing, one would like to know if the Bers slices are pre-compact in this space. It is a fact that if you do not pass to the correspondences, if you only work with the conformal matings, which are these objects on the right side, then this thing cannot be compactified in the space of single-valued maps. There are some topological obstructions, and the obstruction essentially comes from the fact that the geodesic laminations that you get on the boundary of the Teichmüller space are not compatible with polynomials. There's a finite collection of laminations that are group invariant as well as Z to the D invariant. It has to be a huge coincidence for a lamination to be Z to the D invariant and Fuchsian group invariant. That only happens rarely. So in general, going to the boundary of the Teichmüller space amounts to pinching some lamination, and you cannot do that while being compatible with the Z to the D dynamics. However, the world of algebraic correspondences is wilder. There, it turns out, one can actually compactify these Bers slices, and what one would like to see, what one would like to understand is what the Bers boundary correspondences look like. Do you actually get combinations of Z to the D with singly degenerate Kleinian groups and so on? So for all of this, it's important to know pre-compactness. This is the result, and I want to say a few words about it. So we can fix the Blaschke product B to be Z to the D. It doesn't matter, at least for the proof that I'm going to present, or the sketch of the proof that I'm going to present, it doesn't matter. Think of the Blaschke product to be Z to the D, and look at this particular Bers slice here. This consists of all those correspondences which are combinations of Z to the D, and Fuchsian groups in the for a k times punctured sphere. Then this thing can be compactified in the space of algebraic correspondences. What does that mean? What is the what does it mean for something to be bounded in the space of correspondences? It means that when you're going to the boundary of the Bers slice, the group side degenerates, the map side remains the same. In the limit, you still want a correspondence of this sort, and you do not want the degree of the rational map R to drop. These sort of degeneration questions, at least recently, there has been a sort of an emergence of degeneration questions in the rational dynamics world where people want to understand which naturally defined sets of rational maps are bounded. So if you take a sequence of rational maps, in the limit, it can drop in degree, right? You can take this. As n goes to infinity, this thing drops in degree. That's a divergence. That's a degeneration in the space of rational maps. How do I detect such a degeneration? Which naturally defined subsets are bounded in the space of rational maps? Borrowing idea, and this is, there are a variety of tools now to study these sort of questions. So we borrow some tools from that world, purely complex dynamics world, to prove this precompactness result. And the point is, this precompactness essentially has nothing to do with the original question of precompactness of a Bers slice in the quasi-Fuchsian locus. Here you want to prove that the degree of some particular rational map does not drop. So what happens if it dropped? Let me draw a picture and try to explain this. All right, so we have this bound series dynamics here, and we have, say, z to the d here, and we have a mating which is defined, outside this hole. You have a bound series dynamics inside, and you have a z to the d dynamics outside. And you're not changing the z to the d dynamics. And then there is the correspondence plane, which is defined by lifting this whole thing. And in the picture, the group part of it pulls back to some number of disks. And the map part of it, where you have z to the d action, so let me just quote unquote z to the d. This is where you have the map action, and these are the regions where you have the group action. In order to show that right, so this is z to the d, but here you have a sequence of Fuchsian groups gamma n going to the boundary, a gamma n. So as n goes to infinity, gamma n goes to the boundary of the Teichmüller space. So in principle, this thing can get distorted, eventually maybe it's going to a dendrite, I don't know. But you want to show that whatever happens, since I have good control on these two regions where I'm not changing anything, the degree of the rational map will not drop. How do you actually want to prove such a statement? So this is indexed by n. The key thing to note is that a bit of it is classical. You can always require that this uniformizing map, there's a Riemann map from this circle, from this disk to the exterior that conjugates the z to the d action to the action of sigma outside. You can normalize it. You can always say that some chosen point 0 goes to some chosen point infinity, and this map has derivative 1 and no translation, etc., just to make sure that this exterior region is of definite size. And in that case, if you normalize things that way, this thing is rigid. There is a limiting conformal disk in the limit. But the issue is, even if you have, or you can also require that this infinity, say, Rn sends infinity to infinity, so this exterior region goes to some exterior region here. And then you want to say that when I pull back this map dynamics under R, and I get the z to the d region outside, this domain is not shrinking to a single point. this domain is not becoming the whole plane. For a conformal disk, in the limit, three things can happen. Either a sequence of conformal disks can remain a nice conformal disk, biholomorphic to the disk, or it can be a single point, or it could be a whole plane. You want to stop these conformal disks to going from going to the whole plane. And basically one does some sort of an argument by contradiction, and what you need to show is that if this disk was getting too small or too big, then I'll just say a couple of words about it. There's a rescaling limit argument that you have to run. What that means is, if this disk is getting too small, then you want to blow up near infinity and in some coordinate, bring it, if this was getting really small, you blow up near infinity and make that thing a definite size object. And if the opposite side was getting too big, then you blow that part around 0 and make that into a definite disk. And then you play with these things, and eventually you get a contradiction. So these sort of rescaling limit arguments, which purely come from complex dynamics, are used to prove boundedness of these Bers slices. All right, so let me not say anything about this. In the case of n equals 4, for a 4 times punctured sphere, it turns out that all these Bers compactifications are naturally homeomorphic. That's because the Teichmüller space is one-dimensional. However, I should mention that the original proof of Bers uses the fact that a Kleinian group does not admit an invariant line field. That is not known for rational maps, let alone correspondences. We cannot take such a strong theorem off the shelf, so we really use the one-dimensionality of the parameter space. And the idea of the proof is roughly that any kind of discontinuity, so if you take the 4 times punctured sphere, if you go back to this picture, suppose here k is 4, you have a complex one-dimensional Bers slice, you have another complex one-dimensional Bers slice. These Bers slices are naturally homeomorphic. It's just changing z to the d to b. Why should it extend continuously to the boundary? You want to show that if it did not extend continuously to the boundary, then there is some sort of quasi-conformal deformation in the background that's playing a role. And if the parameter space is one-dimensional, then a boundary point cannot admit a quasi-conformal deformation, because a quasi-conformal deformation comes with a Beltrami disk. And you do not have that on the boundary. You cannot have a disk in a boundary. Okay, let me try to end with as I promised, with a purely Teichmüller theoretic application of this entire circle of ideas. Mahan's example will make a reappearance here. So for this, I really need the factor bound series map. So what is my idea? My idea is, or what is my goal? My goal is to generalize, or at least in suitable circumstances, or rather extend the classical Bers simultaneous uniformization theorem. No mention of a Blaschke product or a polynomial here. So the classical Bers simultaneous uniformization tells you that if you take two, say, groups in the same Teichmüller space, then you can construct a quasi-Fuchsian group that combines the actions of these two Fuchsian groups. These two things have to uniformize the same surface. And this whole idea of passing from a group to a Bowen series map, or a factor Bowen series map, in some sense, it gives you a little bit of flexibility. It's a forgetful functor, let's say. It's not a, whatever it is, it's a forgetful object, it's a forgetful procedure. You go from a group to a map, and sometimes it can so happen that you have two surfaces, S1 and S2, that are not homeomorphic, but the factor Bowen series map of S1, or let me say gamma 1, well, okay. Basically, I'm talking about, when I'm writing a surface, I really have the Fuchsian group in my mind. So let me write gamma 1 and gamma 2. And when I say gamma 1 and gamma 2 are not isomorphic, what I mean is that, spell it out. They do not uniformize the same topological surface. They do not uniformize the same topological surface. These are two Fuchsian groups that do not come from the same Teichmüller space, but it can so happen that the factor Bowen series maps of these guys have the same degree. And if you recall the entire mating framework, we never use the actual structure of the surface in the initial version or in the initial steps of the mating, you just try to construct a factor boundary series map from the surface, and as long as the degree of that map was the same as the degree of the Blaschke product, you could combine these two things. So why not try to do the same thing here? So what am I showing here? I'm showing you a factor boundary series map. Where does this left example come from? The left picture. The left picture is coming from this. You take a surface with two cusps, an order 4 and an order 2 orbifold point. So let's try to draw a fundamental domain of that thing. Let's see if I can do it. Order 4. Order 4. So I'll have this, and I want two cusps and an order 2 orbifold point. Right, so it's this. Okay, and my side pairings are like this. Right, if these two things are identified, I'll get an order 4 orbifold point. These two geodesics are identified, so these 2 points become the same cusp. These 2 points become the same cusp, so I get 2 cusps. Since this Mobius map is an involution, I get an order 2 orbifold point here, and there's an order 4 orbifold point there. So this is my surface. And the recipe of passing to, of constructing the factor boundary series map was to pass to a cover, to resolve this higher order orbifold point. So you want to get 4 copies of this thing, and that's exactly what is going to give you the picture that Mahan had. You want to glue 4 of these, so all of it should be symmetric, and it's not a hole, it's a puncture, etc. And for this, you can draw a factor, you can write down its boundary series map. The boundary series map is going to be discontinuous, but so mildly so, then you pass to a quotient, and you get this picture, right? When you pass to a 4-fold quotient, these 3 things, if you just take a cone, this blue line becomes some sort of a horizontal line there, and these 3 things will become the boundary of the domain of definition of the factor boundary series map. What is the degree of this map? The degree of this map is 11, because there are 12 pockets here. That's a combinatorial check. Instead, I could take another surface which has 3 cusps and an order 3 orbifold point. That would mean I want this 3 cusps. So 3 cusps would be this. My identifications are this, these 2, and this. If I identify, this is going to give me an order 3 orbifold point. These 2 points will be joined to give me 1 cusp. These 2 will give me another, and this will give me another cusp. No orbifold point here. I pass to a 4-fold cover. Once again, I get the same picture. There are 4 of them, but I'm gluing 3 copies of them, so I get something defined on 12 pockets. So the degree is once again 11. So the point is, these 2 surfaces, although they are not homeomorphic, they're factor boundary series map. Forgetting the topology on the surface, but only remembering the degree of the factor boundary series map allows me to glue these 2 maps. And I'm going to conformally mate them using the analytic machinery of the Wied integrability theorem. And once again, since the map that we have here, so it's defined. So what have I done here? What is this picture? This picture is basically taking this as a lower hemisphere, this has an upper hemisphere, and gluing them. And then the map is defined outside this triangle. It's defined in the, it's not defined on this triangle, the blue triangle, and on the exterior of this brown, I guess, brown quadrilateral. But wherever it is defined, it's a meromorphic map. It extends continuously to the boundary, and it is an involution on the boundary. So the B involution statement that we had now gives us an algebraic description. One can again lift the whole thing to an algebraic correspondence, which, if you go through the factors, the main point is that the single valued map that you constructed here combines the factor boundary series maps of the 2 surfaces. Then you have an algebraic description. You pull it back by the uniformizing rational map R, just like in the previous setup, and you get a correspondence. I didn't draw a picture, it would be a little messy, but there are finitely many components in the domain of discontinuity. Under the action of the correspondence, they split into two grand orbits. So there are two correspondence orbits. The quotient of one of these orbits by the correspondence will give you this surface. The quotient of the other orbit by the correspondence will give you the other surface. And that's exactly what a simultaneous uniformization or a quasi-Fuchsian does. You get to simultaneously uniformize two different surfaces. And now that you can do it, I mean, there's no reason why you would do it for one. You can do it for all. So the reason I chose a sufficiently complicated example was that I have at least 4 marked points in both cases. So they have non-trivial Teichmüller spaces. You can vary the complex structures on these two surfaces independently, and that will give you a product of the two Teichmüller spaces in the space of algebraic correspondence. And then you can ask exactly the same questions. What are the Bers boundary groups? What are degenerations on both sides, et cetera, et cetera. So yeah, so let me just end with this. Same questions in both settings. What are the boundary correspondences? The limit sets locally connected, double limit theorem. What are the boundaries of the Bers slices? What happens if you leave the Bers slice in this ambient space of correspondences? What do they look like? Thanks to Ponderable. Okay, thank you. Okay. Here, if you fix, yeah, so these vertical curves, if you fix the group and let the Blaschke product vary, so that side is a little harder to study. Okay, so the statement is that this slice is still compact. You get the entire, first I have to tell you what, I've only drawn the space of Blaschke products, but I could look at all polynomials with connected Julia set. That would be like the Mandelbrot set in higher degree. And the point is, you do see a compact vertical leaf, which it's not true that this thing is homeomorphic to the connectedness locus of degree D polynomials. And that again comes from Kirchhoff-Thurston type discontinuity. So just here, the point is you can prove that the Bers slices are all homeomorphic. You cannot say that the boundary extensions are also continuous. The same is true here. If you only restrict yourself to the hyperbolic component, then the map that takes you from one vertical slice to another vertical slice is a biholomorphism, but the boundary extension is not supposed to be continuous. And the reason is, again, similar to the Kirchhoff. It's geometric limits. It's geometric limits being larger than algebraic limits. There is a compactness, yes. There's a compactness. That proof is, yeah, slightly trickier, but there's a compactness.